All right, here we go with section 3.1. That was a little bit of Russia's closer to the heart to start off today's lesson. All right, to begin with, what we're going to be looking at primarily is beginning the study of identities in trigonometry. So we're going to begin with some fundamental identities. We're going to call these the basic identities, and we're going to look at an identity is really just a mathematical equation, and every number value of x, it's satisfied wherever x is defined. So these are what we call the reciprocal identities. Actually, we've already learned these if you think about this. We know the sine and the cosecant are reciprocals of each other, and we know that the cosine and the secant are reciprocals of each other, and the tangent and cotangent are also reciprocals of each other. So that's really what these identities are saying. All right, well, let's prove one of these just to kind of get the idea. Let's prove that the sine of x is equal to 1 over cosecant x. Okay, and the way we're going to do this is we're going to start basically just by writing down the left side of this. So let's start with 1 over cosecant x. And all we're going to do is we're going to replace it with its definition. The definition of the cosecant is r over y. So this is really saying that we're doing 1 divided by r over y, which is saying that we do 1 times y over r because we're dividing fractions. That gives y over r. However, y over r is the definition of the sine. So that is a demonstration of why that works. All of these identities are all basically the same idea. So the idea would be, say for instance, that we know that the sine of x of some angle x, let's say that we know that that's equal to 2/3. Okay, then according to this identity, the cosecant is 1 over the sine. So that would just mean that it is 1 over 2/3, which is saying nothing more than it's the reciprocal. Okay, so that's what all these identities are saying, is they are reciprocal identities. Okay, you can rearrange identities. And one of the things that's kind of important on this too is, like, if you take this basic identity, the sine of x equals 1 over the cosecant of x, well, you can rearrange identities into different forms if you just do correct algebraic procedures. So if we were to multiply both sides of this equation by the cosecant of x, notice what we would get is we'd get a new form of that identity. We would get sine x times cosecant x is equal to 1. So that is really another form of the same identity. So by a same argument, all these things can be derived the same way. And the way I look at this is like this. Okay, we know that the sine and we know that the cosecant are reciprocals of each other. We know that by definition. So the thing is, what happens if you multiply a number like 2/5, and if you multiply it by its reciprocal, well, you always get 1. So really think of these as you're multiplying a number by its reciprocal, so you're always going to get 1 when you do that. Okay, so anytime you're multiplying this out, you will get 1. Those are very simple things to remember. Okay, couple of observations. Any number multiplied by its reciprocal is 1. Okay, the only exception to that would be like if you did the reciprocal of 0. Since the reciprocal of 0 is undefined, you just could not get a value if you multiplied 0 by its reciprocal. But in any other case, you have that. All right, reciprocal of the sine is the cosecant. So that means that we know for a fact that the sine x times the cosecant of x would be equal to 1. The reciprocal of the cosine is the secant. So we would know for a fact that the cosine of x times its reciprocal would be 1. And we know the reciprocal of the tangent is equal to the cotangent. So that would be allow us to conclude that the tangent of x times the cotangent of x equals 1. All right, these are what we call reciprocal identities, and they're very important to remember. Okay, the next thing we're going to move on to is what we call a tangent and cotangent ratios, or sometimes we call these the ratio identities. So there are two of these that we want to learn. The first one is the tangent is equal to the sine of x over the cosine x, and we'll look at a couple of reasons why that is. First of all, one good thing to remember, I'm just going to sketch a unit circle on this, is if you have a point on the unit circle, it doesn't really matter what we choose. Let's just say we're at this point right here on a unit circle, which is 30 degrees or pi over 6, where we have the fundamental point, square root of 3 over 2 and 1/2. Okay? What we know is we know that the sine of pi over 6 is equal to the y value, 1/2. We know that the cosine of pi over 6 is equal to the x value, square root of 3 over 2. And then we know the tangent is just equal to y over x. So therefore, on a unit circle, since the sine is the y value and the cosine is the x value, well, the ratio identity kind of comes out of that then. Okay, so let's do a proof of this. So let's start with proving this, and I'm going to just write down the side that's more complex. Let's write down sine x over cosine x, and all we're going to do is just apply definitions. Okay, so if we were to do the sine of x by definition, what we would end up having on this is we would have the sine is y over r, the cosine is x over r. Really, it'd be better if I looked at these things with just an angle theta in it instead of an x and y. But these ratios and identities can be written with any variable. I just think it's better to write it this way. So anyway, this is a division problem. So we're doing y over r divided by x over r. We divide fractions by multiplying by the reciprocal. And notice on this, the r's would cross out. That would leave y over x, but that's what the definition of the tangent of x is. Okay, so what we'd end up having is we have just proved that this is equal to that value. Again, I'm going to use a sine theta, tangent theta on that. Okay, now moving on from there is, okay, if we know this is true, then it's easy enough to conclude that this is true. And the reason is because the cotangent is just the reciprocal of the tangent. Okay, so if you know that the tangent of theta is equal to sine theta over cosine theta, then it's easy to conclude that the cotangent of theta would be the reciprocal, so it would be the cosine theta over sine theta, like that. Okay, so those are the cotangent, the ratio identities. Next thing we're going to look at is the Pythagorean identities. And there are three forms of these. The one that I'm going to start with is this one, the sine squared of x plus cosine squared of x equals 1. Now I'm going to use thetas on this, or alphas. Let's use like alpha. Let's use a different variable for this, and let's do a proof like this. So actually the proof is real simple. What you do on this is we're going to start our proof just by writing down the sine squared of alpha plus cosine squared of alpha, and then we're going to apply definitions. So we know the sine is y over r. We know the cosine's x over r, so we're just going to work with y over r squared plus x over r squared. And when we work that out, we're going to have y squared over r squared plus x squared over r squared, like that. So we have a common denominator, so we're going to write this as y squared plus x squared over r squared, keeping the denominator. But recall that what we know is from the Pythagorean theorem that r squared is equal to x squared plus y squared. So that means this thing right here is really just r squared, and then r squared divided by r squared is 1. So that's how you can prove that that is true. The other way to look at this is if you looked at this on a unit circle, it's kind of a nice way to look at this. So basically, if you have any angle alpha on a unit circle, and you end up really what you have is the x value is the cosine of alpha, and the y value is the sine of alpha, then this is r, so it really follows straight from the Pythagorean theorem. You kind of end up having a right triangle in a unit circle where this is alpha, the x value is the cosine, the y value is the sine, and that's r, so that is direct application of the Pythagorean theorem. So you would have cosine squared alpha plus sine squared alpha is equal to r squared, and of course in a unit circle, r is equal to 1, so you get cosine squared alpha plus sine squared alpha equals 1. Okay, so now the other thing that I find to be pretty important is it's pretty easy to remember this identity. The other two are a little bit harder to memorize, but it's actually very easy to derive them. So let me show you how to derive them. First of all, let's start by just writing down the sine squared, and again, I'm going to use alpha on this. Doesn't matter, you can use any variable, but since I'm using the XYR definitions, I'm just going to use a different variable name. So we have the sine squared of alpha plus the cosine squared of alpha equals 1, so we just proved that. Well, what you can do to derive the other ones is divide. First of all, let's start by just dividing both sides of this equation by the sine squared of alpha. And I'm going to divide both pieces of the left side by that then. Okay, now when you begin to look at this now, we can apply a couple of identities. Of course, anything divided by itself is 1. And then this thing right here, we learned that the cosine over the sine is the cotangent. So this would really be the cotangent squared alpha. Then we have the identity that says 1 over sine is equal to the cosecant. So this would become cosecant squared alpha. So that shows and proves that identity. So it's real important to learn how to derive the other two. I do that all the time. Now I'm going to derive this other one. So I'm going to write down sine squared alpha plus cosine squared alpha equals 1. And what I'm going to do this time is I'm going to divide everything by cosine squared alpha. And the other identity will come out of that. So let's go ahead and do that. And let's kind of talk through what we have here. So the idea would be that this thing right here would be the tangent, because we just learned that identity. So sine over cosine is tangent. Therefore, sine squared alpha over cosine squared alpha is tangent squared alpha. Okay, this thing right here is 1. And then 1 over the cosine is the secant. So that would be the secant squared alpha. Okay, so that proves and derives that identity like that. Okay, so it's pretty important that you learn how to take the original identity, which is this one, and then derive the other two in case you forget them. And I forget them all the time, so I derive them constantly. Okay, now what we're going to do is, next thing, we're going to use some of these identities to derive and simplify expressions. So this problem says write the expression in terms of sines and cosines. So we're going to do a couple of substitutions on this. First of all, we know that the secant of x is equal to 1 over the cosine of x. That's a reciprocal identity. We also know that the sine, now the sine, with that one, we don't really have any of the basic identities that can translate that into a cosine, but it doesn't matter. What we're wanting to do is write this so the expression has nothing but sines and cosines. So what we're going to do is we're going to replace the secant with what it's equal to, 1 over cosine, and then we're going to just leave the sine alone. And what I'm going to do on this is I'm going to go ahead and just get a common denominator and add the two fractions together. So we'll do a little bit of simplification. So we have a common denominator of cosine x, so I'm going to multiply the top and bottom by the cosine x. Okay, so when I do that, we are going to have 1 over cosine x plus sine x cosine x over cosine x. Now what I can go ahead and do is just combine those into a fraction, and then we're simplifying. So this is kind of a typical thing that we do a lot in trigonometry and higher math is we sometimes write things in terms of one or more trig functions. So an answer to this problem would be this. You really can't go any further than that, and technically you're just getting a common denominator to do that then. Okay, now the next problem, again, we want our answer to have just sines and cosines in it and nothing else. So the idea with this one is going to be, there's a couple of things that will be helpful. First of all, the tangent of x is equal to the sine x over cosine x. That's one of the reciprocal ratio identities. And we also know that the secant of x is equal to 1 over the cosine of x. Now there's a couple of ways to go about doing this problem. The first way I'm going to do this is like this. I'm going to just replace things. I'm going to do this in a little simpler way in a minute. So let's go down here at the bottom and let me show you two ways to approach this problem. I think the second way I'm going to do this is a little simpler. So let's start by writing down the expression tangent x over secant x, and we're going to replace the tangent with what it's equal to. It's equal to sine x over cosine x, and then we're going to replace the secant with what it's equal to, which is 1 over cosine x. Now, we need to algebraically simplify this a little bit. So this is a division problem, so you could write it as sine of x over cosine of x divided by 1 over cosine of x, and then you could multiply by the reciprocal. So this is really the sine of x over the cosine of x times the cosine of x over 1. What happens is the cosines divide out, so you'd have sine x over 1, which is just equal to the sine of x. So it turns out that this expression is really the same as just the sine of x. They're mathematically equivalent to each other. Now there's another way you could do this problem. I always like to show students this way because I find it a little easier to do it this way. So you could break this fraction up like this. Tangent x over 1 times 1 over secant x, like this. Now you can replace a couple of things. Well, the tangent is just the sine over the cosine. You don't need that over 1. And then this is the cosine. 1 over secant is the cosine. So you get the same result a little bit quicker that way. You don't have to deal with any complex fractions. So that's the way I like to do fractions a lot of times, is break them up into a multiplication problem, and then I can simplify it a little easier that way. Okay, now the next couple of problems that we have on here is we can always take a trig function, and we should be able to express it in terms of another trig function. So we're going to try to start with the sine of theta, and we're going to express that in terms of a cotangent. And you have to be kind of smart in the way that you do this. So one of the things that I'm going to think about here, I'm going to go up to this previous page and point your attention to this identity. Okay, we end up having 1 plus cotangent squared equals cosecant squared. So I'm going to write that at the side. 1 plus cosecant squared x is equal to cotangent squared x. And I'll kind of talk through why I am thinking that that identity might be helpful. So I think I wrote that backwards, didn't I? I wasn't paying attention. So let me fix that. That should be 1 plus cotangent squared x equals cosecant squared x, like that. I forget that identity all the time, but I showed you a quick way to derive that when you need to. Okay? All right, now my thought process on this is, okay, this thing right here is really 1 over sine squared x. So I'm trying to make a connection between this and a cotangent. But this is only a sine of theta. So what I'm going to do is I'm going to do this like this. I'm going to use a clever trick on this. I'm going to say, well, I could change this to sine squared theta as long as I'm doing the square root of it. And then I got to have a plus or minus because I've got to encompass all of the different signs. that you would have in the different quadrants. So I'm going to start the problem this way, okay? Then what I'm going to do is basically one way that you could do this on this is you could replace a couple of things on this like this. So you could say, if you wanted to, just go like this. You could say, well, I'm trying to make this into a cotangent, so I could say plus or minus square root of 1 over cosecant squared theta. Okay, like that. Now, it's pretty simple to just plug in and then clean up the algebra. Okay, so now what I'm going to do is write this as plus or minus, and I'm going to do a substitution. I'm going to leave the 1 the way it is, and what I'm going to do is a real simple trig substitution. We know that the cosecant is equal to 1 plus cotangent from the Pythagorean identity. So I'm going to replace this with 1 plus cotangent squared theta. And see, by doing that, I have changed this sign into an expression that just has a cotangent. However, what I'd like to do is kind of simplify this a little bit. So, of course, the square root of 1 is 1. So we're just going to have 1 over the square root of 1 plus cotangent squared theta. And let's go ahead and rationalize the denominator. And then we'll have a little bit better answer. So I'm going to just multiply the top and bottom by 1 plus cotangent squared theta. And then we should have a simplified answer to that problem. Okay? So let's see, when I do that, the final answer is going to be plus or minus, multiply the numerator, you're going to have 1 plus cotangent squared theta all over, and then this rationalizes the denominator, so it's just going to be 1 plus cotangent squared theta like that. So that's it. Okay, we have rewritten that in terms of a cotangent. This exercise comes in handy with some things that you might do in calculus, with integrals and differentiation and different types of things you'd learn in a calculus class. So that would be the one way to solve that then. All right, so this really, believe it or not, this messy expression right here is really the same thing as the sine of theta. They're mathematically equivalent. Okay? Now what we're going to do on this next one is a similar thing. We're going to start with the cosecant, and we're going to try to write this so the answer just has a secant in it. So again, let's kind of go back and let's look at what identities that we might have to help us with this. So I'm going to scroll up to this previous page and let's look at this. So let's see, we're trying to turn a cosecant into a secant. Okay, well, here's a secant here. That might come in handy. There's this basic sine squared plus cosine squared also might come in handy because you can change a cosine into a secant, and you can change a cosecant in a sine into a cosecant. So one of those identities might actually come in handy. So I'm going to approach this in a couple of different ways. All right, so the way I'm going to start this, I'm kind of thinking that, well, we have the basic identity, sine squared theta plus cosine squared theta is equal to 1. And you could rearrange this like this. Actually, let me look at it this way. You could move the cosine this way. So you would have sine squared theta equals 1 minus cosine squared theta. Okay? Now, if I put both of these things, over 1 like this, well, you could change this thing to 1 over cosecant squared theta. And then this thing could be 1 minus, and then that would end up being 1 over secant squared theta. So there seems to be a connection between these two things using that identity. You can change the cosecant into a sine, then you can change the sine into a cosine, which ultimately goes to a secant. So that's kind of my thought process I'm going to go through. So what I'm going to start with on this is I'm going to start by writing this again as plus or minus square root of cosecant squared theta, like that. Okay, then I'm going to write this as plus or minus 1 over sine squared theta, like that. then I'm going to substitute an equal for an equal. So if you look at this, what I'm going to do is the sine squared theta is the same as 1 minus cosine squared theta. That comes from the basic Pythagorean identity. So my next step is I'm going to do this. I have plus or minus, and I'm going to write the square root of 1 is 1, so I'm going to put 1 over, and I'm going to replace the sine squared with 1 minus cosine squared theta like that. Okay, and then when I do this, I can also utilize this identity. So basically the cosine squared theta is 1 over the secant squared theta because they are reciprocals. So the next thing I'm going to do is I'm going to do that substitution, and by doing that, then I've really accomplished my goal, and then I need to just kind of algebraically simplify this. So I'm going to move this over here, and we'll clean this up and try to get a final answer on here then. Okay, so this is now going to be plus or minus 1 over the square root of 1 minus 1 over the secant squared theta. So we've actually accomplished our goal. We've changed the cosecant into the secant. Now we just need to clean this up because we have some complex fractions. So I'm going to rewrite this as plus or minus 1 over, and it looks like we have a complex fraction, so the idea is we need to try to clean that piece up. Well, whoops, I'm writing that wrong, so let me correct that. So I'm going to get that erased, and then let's put this in here and let's deal with the complex fraction. So this is 1 over secant squared theta like that then. Okay? Well, what we can do on this now is you can actually go underneath this radical if you want to, and you could get rid of this by multiplying like this. Now what you could do on this is the idea would be you would need to multiply under that radical by a secant squared theta, okay, to get rid of that when you do that. So I'm going to put a parenthesis around there, and we're going to do that. Okay, so I'm going to multiply under that radical by secant squared alpha to get rid of that. Okay, now by doing that though, I've changed the problem. So I have really multiplied by, what I just really did is I multiplied by the square root of the secant squared theta. So I have to do exactly the same thing to the numerator. I have to do the same thing. Okay. So you could write this if you wanted to. It might be a little bit more clear. I'm going to erase this and write it more like this to show you technically what I'm thinking about here. So what I'm doing is I'm really multiplying the denominator by the square root of the secant squared theta. That way it'll go under that radical and then cancel out. Then I need to do the same thing there. Okay. So let's take that step and then let's put this together then. So what we're going to have is plus or minus the square root of secant squared theta, which of course is just going to be secant theta anyway. And then that's going to be over, and then you've got to do a distributive property, so you're going to do that times 1, okay? And when you do that, see, that's now under that radical, so you would end up just having that times that would be secant squared theta, like that, okay? And then when you multiply this by that, they cross out, so you'd be left with 1 like that then. Okay? Now the reason that I'm multiplying that by a square root of secant squared theta is so that it will go under that radical, and that's real important. So now really, we could just get this answer. We'd have plus or minus secant theta all over the square root of the secant squared theta minus 1, and then that just leaves me with rationalizing the denominator. Okay, so when I do that, let's go ahead and rationalize denominator, then we'll have a good simplified answer to the problem. So I'm going to multiply by square root of secant squared theta minus 1 to the top and bottom. And then that way I'll have a rationalized denominator, then I'll have a good answer to this problem then. Okay, so the final answer we would have is secant theta plus or minus times the square root of secant squared theta minus 1 all over, and then that would be rationalized, so that's now secant squared theta minus 1. Okay? So that would be your solution to that problem then. All right, that can be a little tricky. It takes a little practice to learn how to do this, but you have to work with the correct identity and work out things correctly algebraically. The big part of this problem was getting rid of that complex fraction, so I have to multiply by the square root of secant squared theta to accomplish that, doing that both in the top and the bottom. So you want to study over this and practice these a little bit. Okay, so moving down to the next page here, we're going to do a little bit of algebraic simplification. So one of the things I'm going to do on this is this kind of prepares you for proving identities that we're going to do in the next section. And these kind of things, you do work a lot with identities in calculus, so we're trying to help students who are going in that direction. So here's some useful identities on this. First of all, the cotangent of x is equal to the cosine of x over the sine x. That's going to come in handy. The other thing is the secant of x is equal to 1 over cosine x. So I'm going to just substitute in these identities like this. So to begin with, I'm going to take the cotangent and I'm going to replace it with what it's equal to. Then I'm going to take the secant and I'm going to replace it with what it's equal to. And then we'll just see if we have any algebraic simplifications we can do. All right, so the cotangent gets replaced with cosine x over sine x. Okay, the secant gets replaced with 1 over the cosine of x. Then I'm going to leave the sine x alone. And notice on this you have several cancellations that you can do. So a cosine over a cosine, of course, is really 1. A sine over a sine is also 1. So that means the answer to this problem is just equal to 1. Okay? Now that's the way that I want you to do this. You can also kind of look at it this way. This also helps students understand this. The cotangent is x over y. The secant is r over x. The sine is y over r. So if you noticed on this, what would happen is, of course, everything would cancel out. You would just remove those common factors and get 1. I don't really like you doing the problem that way, but it does help you to understand that, because partially what we're learning how to do is use identities and not just the definitions, okay? So let's see what we got on this next one here, and let's see what kind of ideas we might come up with. There's a few things that I see on this. One identity that's probably going to come in handy is sine squared x plus cosine squared x equals 1, because I do see a cosine and sine squared in there. We also have cosecant x equals 1 over sine x. So we might be able to utilize these in some way. So I think what I'm going to probably try to do on this, and there's more than one way to do these, you got to understand that. Sometimes you just have to play with it and see what happens. So what I'm going to do is I'm going to work with this cosine, and what I'm going to do is take this identity and I'm going to solve it for cosine. So I'm going to move that sine over like that to rearrange that identity, so it says cosine squared x equals 1 minus sine squared x. And then I'm going to do this substitution. I'm going to replace the cosine with what it's equal to in that identity and just see what happens. Okay. Then I'm going to do this substitution. I'm going to replace the cosecant with 1 over sine, and then we'll just kind of see what happens here. Okay. So let's go ahead and do that. So this is going to be cosecant squared x. We're going to replace that with 1 minus sine squared x. Going to leave the sine squared x alone because there's going to be some simplification I can do in there. And then the cosecant gets replaced with 1 over sine. And you don't have to do this. If you see what I would like you to see, you could bypass that anyway. So what you'll find, of course, is that removes, so that will be plus 1. Like that. And then one thing you could do on this is you can take this fraction and you can split it apart. So there's more than one way to do this. You could say 1 over sine squared x, and then you could say minus sine squared x over sine squared x, like that. Okay, and by doing that, you would have some algebraic simplifications that you could do. Okay, so notice what happens is 1 over sine, if you look at this piece right here, just this part right here, 1 over sine is cosecant squared. So that's going to get replaced. So we'll end up having, this becomes cosecant squared x. This whole thing right here becomes 1 plus 1. So those, of course, cross out to go to 0. So it looks like a simplified answer of this problem would be cosecant squared x. Okay, and that's one way to look at it. There's, usually more than one way to look at these problems, but that would be one way. So you're trying to algebraically simplify these. Okay, so let's look now at what we mean by even and odd functions. So I want to do a little bit of a review on that. So let's look at what even functions look like. First of all, the definition of an even function is anytime that you replace x with negative x, you just get the same function value back. The way to really understand this technical talk here is just to look at a couple of pictures of how points go. So what I'm going to do is just draw a coordinate system, and I'm going to give you some examples of some points on this that would represent what an even function is. So let's say, for instance, that you have a point let's say you have a point 2, 4. Okay, according to an even function, what an even function really means is if you replace this x with an opposite, then you get the same y value back. So what it means is if you take this point and replace it with a negative value, then you get the same y value like this. So these 2 points would be examples of the kind of points that fall on an even function. And notice what you have on this is they are symmetrical about the y-axis. Okay, so an even function would be some sort of a function that every single set of points on there would follow this. Okay, another example would be like if you had a point 1, 1. Okay, well then you would have to have a point negative 1, 1. Again, the idea is if you have the opposite x's, same y. So one of the best ways to understand even functions is just think of opposite x values, same y values. Okay, that's a real key way to just, in words, understand what even functions look like, and then they're going to have symmetry across the y-axis. So that's how that goes. Okay, let's look at an example of a odd function now and try to go over how that goes. So an odd function, it says if you have an opposite x, then you have the opposite value of y. So a good way to help you understand this would be, again, just to do a graph. I'm just going to do a coordinate system again, and we'll look at some basic points. So let's say I'll just use as an example the point 3, 2. Okay, in order for a function to be odd, then it would work like this. If you have an opposite x value, then you're going to have an opposite y value. So that's going to imply that you get an opposite value of y. So this point right here would translate like this. The 3 would become opposite, and the 2 would become opposite. So what you would end up having is a point negative 3, negative 2, like that. Okay? Another example might be you have a point 1, 4. Well, then you would also have a point negative 1, negative 4. Like that. So you're going to kind of notice that what happens is, first of all, they are symmetric about what you call the origin. So the idea would be, the way you can kind of visualize symmetry about the origin is to think about it this way. So if you took this point and moved it over here, then if you moved it across that axis, so if you move it over the y-axis, then move it across the x-axis, then it should match up. Okay, so those 2 points right there are symmetric in that way. Fold over y, fold over x, they match together. The other 2 points work the same way. If you fold over y, that point would go there. Then if you folded over the x-axis, that point would go there. So it's just kind of a matter of going over both axes. That's what we mean by origin symmetry. Okay. So again, the way that you want to look at an an odd function is think of it as opposite x values will generate opposite y values, like that. And every point on that function is going to be like that. Okay. All right, now let's move on and let's look at something specific before we get into the trig functions. I want to do just a review of a basic odd function on this. So the idea is if you have a point, if the function's odd, then it's the basic thing that you have an opposite x value and you also have a opposite y value. Okay, if every point on the graph of that function has that characteristic to it, then it's going to be an odd function. Okay, odd functions are symmetrical about the origin, meaning if you fold over x and y, then the points should match perfectly. All the points should. So I'm going to just review a real simple example of an odd function. Okay, so let's look at f of x equals x to the third. We're going to go over and make a table of values, plot this, and then I think this will help you see how this goes. So we're just going to take these x values. You can take any number to the third power. So your domain of this function is going to be all real numbers because you can take any number and raise it to the third power. So we're going to just work out each of these numbers and we're going to multiply them out to the third power. And then we're going to plot the points and then we're going to kind of analyze the symmetry and see if this has the same kind of characteristics we think. So if you work out negative 2 to the third, that's negative 8. Because again, what are you doing? You're multiplying out 3 negatives, so you do get a negative. Then this is negative 1, this is 0, that's positive 1, and that's positive 8. Okay? So if you look at this, if you just kind of look at the idea on this, notice how these points go. Okay? Those are opposite x's, opposite y's. Here's another pair of points. Look at this. Opposite x, opposite y. And 0, 0 is just kind of neutral since it's at 0. So now let's go ahead and let's plot these points and label these so we can kind of analyze this graph. So we have a point negative 2, negative 8. And I'm going to have you write that point on there too. Okay, now notice we also have a point 2, 8. So if we make x opposite and y opposite, then you have a point like that. Okay, then we have negative 1, which would be there. And notice if we have an opposite x, we ended up with an opposite y, so that point would go right there. And then finally we had the point 0, 0, like that. Okay, so if I was to go through and graph this function, then it would look kind of like this. Okay, with that type of structure like that. So that would be an example of an odd function. And it's got the symmetry that we would expect on there. So the idea would be is if you took any of these points, like if you took this point, and if you took 2, 8 and moved it over the y-axis, it would basically go there. Then if you took that point and moved it over the y-axis, the x-axis, they would match together perfectly. So that's an example of that. Now I'm going to do something on this graphing calculator and just pull this up for a second and graph this function and show you how the table of values, just to kind of reiterate the idea on here. So I'm going to put in y equals, going to clear off what I have, and I'm going to put in x raised to the third power, and I'm going to go just to a standard window and graph that. Now the other thing I wanted to show you is if I go second graph, this will pull up a table of values, and this should show that symmetry real well on here. So notice you have negative 4, negative 64. negative 3, negative 27. So if I scroll down a little bit on this, look what you got. You have opposite x, opposite y. Opposite x, opposite y, and it will be that way through every point on that function. Okay, so that's the idea. Okay, so that's an example of an odd function. Let's do an example of a simple even function by kind of applying the same process. So I'm going to look at the function f of x equals x squared and analyze that a little bit. So even functions have this characteristic. If you have a point, then if you take, and this is wrong, so I need to correct this, and this is, you should have a point negative a, b. So the idea is opposite x, same y value. That's the way that you want to think about even functions, is every point, if you have an opposite x, the y values are unaffected. Okay, and then these are going to be symmetric about, odd functions are symmetrical about the origin. I think what I meant to put on this is even functions are symmetric about the y-axis. Okay, so let's go ahead and let's generate this then. So let's just analyze some points. The idea is the domain of this function is all real numbers because you can square any number. Any number can be multiplied by itself, so you'd have that. Okay, so now what I'm going to do is just square each of these numbers. So I got negative 2 squared, negative 1 squared, 0 squared, 1 squared, and 2 squared. And then if I work out the details, that's 4, 1, 0, 1, 4. So notice on this, when you had an opposite x, what did you have? You have the same y value. Opposite x, same y value. Okay, so let's go ahead and plot these points. So we have a point negative 2, 4. So we want to get that plotted and labeled. We have a point negative 1, 1. We have a point 0, 0. We have a point 1, 1. So notice on that we have opposite x's but same y. Then finally we have a point 2, 4. So again, opposite x, same y. Now, if you're going to go through and plot this out, of course, this is a quadratic function. This is a parabola. So notice that this is going to be symmetrical about the y-axis. Even functions always are. Okay, so that would be the idea of how even functions work. Pretty simple thing to look at and try to learn it this way. Opposite x, same y. Okay, on every single point on the graph. Opposite x, opposite y. Okay, so again, if I pull up my calculator, if I just change this to the graph of x squared, of course I get the parabola we're familiar with, but if you were to look at your table of values, you can use this to help you understand. So notice you have a point negative 416. So if I scroll down a little bit, I've got 416. So these y values are the same whenever the x values are opposite. So that's what you want to get solid with. Okay, now one of the reasons I want to spend some time reviewing that is because we have what we call odd and even identities in trigonometry. So we want to be sure that we're clear on how these go. These are the odd and even identities. So basically, there are two even functions in trigonometry. There are the cosine and the secant are examples of even functions. Okay, they're even functions. Their graphs are symmetrical about the y-axis. Then you have four odd functions. The odd functions are the sine, the cosecant, the tangent, and the cotangent. Okay, now before I go over anything on this, you can think about the graphs of these things from your knowledge of the graphs will help you with these. So the thing on this is, notice how the structure goes. If you have even functions, basically the idea is if you have, and then these are wrong, I didn't cut and paste very good. These things need to be corrected. On an even function, it goes like this. If you do the cosine of the opposite angle, you get the same y value back. And then same thing on the secant. You would say secant of opposite x is same value like that. So these are the correct ways to write the identities for the odd functions. And then these are the correct ways to write the identities for the even functions like that. Okay? And again, don't memorize those things, build them. Here's what I always tell students to do on this is if you have an odd function, and I keep reiterating this, oh, what happened? Okay, I think I'm still recording, so I think I'm okay. All right. Computers always surprises. Every time you mess with a computer, something happens. All right, so the idea is if you have an odd function, and I think I'm still recording, aren't I? Yeah, I'm still recording, so I think we're good. Okay, so an odd function, think of it as opposite x, opposite y. So here's the idea, okay? You have a sine of x equals a sine of x, obviously. But what you're doing on an odd function is you're changing this to the opposite. So you have opposite x, now you get opposite y. Okay, like that. Now you don't change that second x like this. This is opposite x. Okay, you've changed those x values to opposites, but the y values turned out to be the same. The idea is that's understood to be positive, that's negative, like that. Now if you have an even function, if you just remember this, opposite x gives same y, then you can build the identity this way. So the two even functions are the cosine and secant. So obviously the cosine of x is the same as the cosine of x. But if you change this angle to a negative, then you do not change that sign. It's the same. Okay, so that becomes the same. On an odd function, this becomes opposite. So that's the idea. So that if you get that in mind, that'll help you build the identities so you don't just blindly memorize those. Okay, now I'm going to look at some graphs on this. Now these are even functions right here. Man, I did a terrible job of typing this thing out. These are even functions. Right, hold on. No. This is how this goes like this. So let's see. One of the things I do a lot of times when I type stuff is I cut and paste, and then I forget to change what I pasted. So this would be examples. First of all, these graphs are not labeled right. These are the graphs. You want to put this on here. This is y equals sine x, and then this is the graph of y equals cosecant x. And what I want you to notice on this is these are odd functions. So this is the graph of the sine and cosine, like that. Those are odd functions. So I think I meant for this to be labeled as sine and cosine. So they're odd functions. So notice that they are symmetric about the origin. So I'll just give you a couple of examples on this. Like for instance, this point right here probably is representing the point pi over 2, 1. So we know on a unit circle, for instance, that at pi over 2, you have the point 0, 1. So the sine is the y value, so it's 1. So notice also this point becomes negative pi over 2, negative 1. That's how odd functions work. Opposite x gives opposite y. So you would find that on both of these graphs, every point would have that kind of symmetry to it. So you can think of taking a point, like for instance, if you took this point and you moved it over the y-axis, then if you moved it over the x-axis, it should basically match up. So that would be an example of odd functions. So the sine and cosecant are odd functions. You can tell by looking at the graph. Okay, this next one is a couple of even functions. Now this is the graph of the cosine, is the one in blue, and then the one in green, of course, would be y equals secant of x, and these are even functions. These are the only two even trigonometric functions. So notice on this, let's look at a couple of things here. So for instance, this point right here on the cosine is the point 0, 1. So we know the cosine of 0 is equal to 1 because on a unit circle, at 0 radians, you have the 0.10, and of course the cosine is the x value. Well, we would expect on an even function that if you changed the x value to opposite, you would just get the same value. So that's probably not the best example. Probably if we had another point like this, notice this point right here would be reflected over the y-axis and it'd be the same value. It'd have the same y value. So this graph is pretty clearly symmetric about the y-axis as an even function is. So that would be one way to help you remember that the secant and cosine are even functions because they're the only graphs that are symmetric about the y-axis. Okay, and then here is the, what in the world? I don't know how in the world that thing's there. You need to scratch that out. This is the graph of the tangent. Okay, so this would be the tangent graph. And notice on the tangent graph, I'll just give you a couple of points here. Like for instance, one thing that we know on a tangent graph is in terms of radians, at pi over 4 radians, the tangent's 1. So we would expect, since it's an odd function, for the point negative pi over 4 negative 1 to be on the graph. And notice that it is. So this point is pi over 4 1. This point is negative pi over 4 negative 1. So it's symmetric about the origin. So a tangent is an odd function. You can look at the graph to determine that. And then the cotangent would work out the same way. Okay? All right, so just kind of to summarize this, what you want to remember is the even functions are the cosine and the secant, and then the odd functions are the rest of them, which would be the sine, the cosecant, the tangent, and the cotangent. So those are all of your trig functions, and that's how they work out. Okay, so we're going to work a little bit now with working out and determining if functions that are really algebraically put together are odd or even based on what we know. Okay, so the way that you always determine if a function's odd or even is you do this. You find f of negative x. So what we're going to do to begin with, we're going to take this function, and where you see x, you're going to replace those x's with negative x, like this, and work that out. So what we're going to get is cosine of negative x times cosecant of negative x. Now we're going to work this out a little bit. So we're going to use the identity. So first of all, the cosine is an even function. So that means the cosine of negative x is just equal to itself. The cosecant is an odd function. So that means the cosecant of negative x is the opposite, or negative cosecant of x. So what we're going to do is we're going to do a couple of substitutions like this. This gets replaced with this because it's an even function. This gets replaced with this because it's an odd function. Okay, so we're going to do that replacement and work this out. So this becomes cosine of x. This becomes negative cosecant of x. Now, if you put this together, let me just write this over here. I'm going to put that negative in front. You're really taking a positive times a negative, so you get negative cosine x times cosecant of x. And what this means is if you compare this to the original, that they are opposites. So this is going to be equal to the opposite of the function. Okay, so notice that, and this is what you always got to do is when you test to see if something's even or odd, is you look at it this way. You look at the original, you look at the final after you replace x with negative x, and you determine if they're the same or opposite, or neither. So in this case, they are opposites. Okay, so since this turned out to be the opposite of the function, that means that this is an odd function. Okay, so that's how you would analyze and prove that. All right, the idea also that you can do on this, now that's the mathematical, the analytical way to do this. You can also look at your graphing calculator as you're working these out, and this will help you to understand all of this better. So if you just put in, and let's make sure we're in radian mode here, and let's just put in y equals, let's put in what we just did. We did the cosine of x times the cosecant of x, and you have to put the cosecant of x in as times 1 over sine of x, like this. Now if we graph this, if we set our window up just to go like, let's say negative 2 pi to 2 pi, and maybe by a scale of pi over 2, and then let's just keep the y values this way. So if I graph this, let's see if this looks like what we'd expect an odd function to look like. Okay. All right. Clearly on this one, if you were to go through and look at this, and you know these points right here, for instance, this point right here, you reflect it over y, then reflect it over x. It matches. And if you looked at your table of values, you should see, it might be a little hard to see on this one actually. It's probably real hard to see on this. But let me just give you kind of an example. Let's trace at a point. So let's trace at x equals 1 and see what comes out. So we have a point 1.64. Okay? So if I did that backwards, if I put in negative at 1, so if I put in trace at negative 1, I should get the opposite y value, and I do. So if you traced at all of the points, you would always find that you have that symmetry. So that would verify that that is a odd function graphically. Okay, that doesn't really verify it, it just demonstrates this is how you verify it is algebraically. Okay, next problem we're going to do like this again. You always just replace the x and replace it with negative x. So f of negative x is going to be sine of negative x squared, like that. So we know that if you square a negative number, it just becomes a positive. So that takes you back to sine of x squared like that. So that's the same as the function. So what we just proved is if you look at these two things, the original function turned out to be the same, okay, after we replaced x with negative x. So what we really just did on this is we just showed this. We showed opposite x gave same y, same function value. So that means that's an even function, okay? All right, so if you were to look at this one on a graphing calculator, let's take a look and see what this looks like. So we would put this in like this. We would say sine of x to the second power. And let's see if this looks like what we'd expect an even function to look like. Wow, that's a real interesting one like that. Well, it does look symmetrical about the y-axis. Definitely, if I just type zoom in, for instance, and press enter, you'll see it a little bit better. I think it's pretty clear to tell that piece of the graph right there is very clearly symmetrical about the y-axis. So notice if I say I traced at 0.5. What? Must have an error on that or something, so let me try that again. Okay, let me zoom back out on that again. I need to be zooming out. Come on, graphing calculator, what are you doing? Whenever it does this little thing right there, it means it's stuck. So sometimes a good idea to just turn the calculator off if you can, and then start it over again. I do that all the time. Sometimes these calculators get stuck. So when we do this and just do a graph in, I can't see what my window was. Yeah, I messed my window up. So let's just go 2 pi, back to 2 pi, and let's do the y's. Let's do the y's actually like -2 to 2. I think we'll see it better. Now let's graph it and let's take a look at it. Wow, that's really weird. That's a cool graph though. So, but my point that I was going to try to show on this is like if I traced at, if I pick a value, like say I put 0.2 in there, okay? 0.2, we have 0.0399. Well, if I trace at -0.2, then I should get the same y value. So this is clearly symmetrical about the y-axis, okay? All right, so use your calculator to kind of help you understand the graphical relationship. So it is symmetrical about the y-axis, as we would expect since it's an even function. Okay, let's go through and do something on number 19. We're going to start this the same way. So we're going to replace, and that really should have said cosecant of x. So this is going to be 3 minus cosecant. Replace the x with negative x, and then work it out. Well, the cosecant is an odd function. So since it's an odd function, that means the cosecant of negative x is the same as the opposite of the function. So you would have that. So what we're going to do is we're going to replace this with this. And then we're going to see what we get out of this then. Okay, so this is going to be 3 minus, now replace this with negative cosecant of x because it's an odd function. So that will give 3 plus cosecant of x like that. So what we're going to do is we're going to just compare the original function with the one that we ended up with, and we're going to see if there's 3 possibilities. Either they're the same, they're opposite, or they're just totally different. So f of x was 3 cosecant of x. That's what f of x is. So we just showed that f of negative x is 3 plus cosecant of x. And they're different. They're not opposites because the opposite of f of x would have to be negative 3 plus cosecant of x. So that would mean that it's not the opposite, so it can't be an odd function. Clearly, they're not the same. So this answer would just be neither. And what you would find on this one, if you did this on the graphing calculator, just to kind of analyze this, you would put this in your calculator like this. You would put 3 minus 1 over sine x. And if we graphed that in the same window, you're just not going to get any of the symmetries. Okay, that doesn't look like it's symmetric about y. I can tell it's not symmetric about x or the origin, so it's going to be a neither. Okay, all right, so that's how that works out. Now we're going to do a little bit of algebraic simplification on these last 2 problems to finish this up. So one thing that you're going to see on this is if you see a cosine of negative x, think of it this way. We know the cosine's even. The reason the cosine is even is because, look at the graph. The graph, you can tell, is symmetric about y. That's one way to remember that. So that means the cosine of negative x is the same as cosine of x. So what we're going to do is we're going to replace this with this, and then we're going to use identities to see if there's anything else we could do on this problem. So we're going to have sine squared x minus 1. Now let's replace that with cosine of x. Okay, now there's a couple of things that might come in handy on this. One thing that you could consider, let's utilize this identity. So we're going to look at sine squared x plus cosine squared x equals 1. Now, my thought process on this is I'd like to take this sine and turn it into a cosine. So I can take this identity and I can rearrange it so I get sine squared x equals 1 minus cosine squared x. Okay, so I'm going to make this substitution next. I'm going to substitute this with this. Okay, when you're working with identities, you start substituting equals for equals a lot. So replace this with 1 minus cosine squared x, bring down the minus 1, and leave the cosine. Now, how did I know to do this? I didn't really know it was going to work out this way, but I just had an idea, so I tried it. So I'm going to get those to cancel, so I'm left with negative cosine squared x over cosine x. And you could write this like this. A cosine squared x is just a cosine times itself. Okay, so one of those is going to divide out. And when I do that, you would just end up with the final answer on that as negative cosine of x. Okay, so we're going to get into some algebraic simplifications in this section. So that would be a simplified answer. Okay, all right, now if I move on to this next problem here and work with this a little bit, let's see if there's any ideas we might have on that. Well, I see a tangent So one thing we learned is the tangent of x, we have the ratio identity that it's equal to the sine x over cosine x. So let's start that way and let's just see what happens. So let's leave the cosine alone. Let's leave the sine alone. And let's do this substitution and just see where it leads us. So we're going to substitute the tangent. We're going to replace it with what it's equal to. Okay, so we're going to go ahead and put that in, see what we get. So let's write that as sine x over cosine x, like that. And I'm going to put the sine x over 1 and multiply this fraction now. So I'm going to bring down the cosine x. This multiplies out to give sine squared x over cosine x. Now I need to think about getting a common denominator and adding fractions. Okay, so I'm going to do that and work with that a little bit. Okay, so I'm going to put this over 1 and get a common denominator. The common denominator is the cosine, so I'm going to multiply this by cosine x over cosine x, and I'm going to bring down this so it says sine squared x over cosine x, like that. Okay, so that this fraction becomes, when you multiply it straight across, becomes cosine squared x over cosine x. And since we got a common denominator, we're going to just add those together. Okay. All right, well, we keep the denominator, so that's cosine x. And then we combine the numerator, so that's cosine squared x plus sine squared x. Okay. However, we have the identity that we learned that says sine squared x plus cosine squared x equals 1. So we're going to do a real simple substitution. So this gets substituted with 1, and then we have just a couple more things to do. So from here, I'm going to write this as 1 over cosine of x. But we have the identity that says, since the cosine is the reciprocal of the secant, then we have this identity. So what we're going to do is we're going to substitute this with what it's equal to, and then that should be as simple as we can write this. So the final simplified answer would be secant of x. Okay? So it turns out that this expression is the same as that expression. They're mathematically equivalent. Okay? So this is a section that it can be kind of challenging for students because you're starting to work with identities quite a bit. So you got to work with this stuff and practice it. So this will close off this idea with identities, kind of the introduction. So hopefully this will go well for you, and hope you enjoyed the presentation.